This is section 2.3, expected value of random variables. So our expected value is a measure of the average value for a random variable. We can think of the expected value as like a weighted average, okay? Or sometimes we think of it as a long-term average or long-run average. And we often call the expected value the mean of our random variable. So if you want to find the expected value for a discrete random variable, okay, to do expected value, we do the e with the little x, or with the capital X. Okay? And we do, if we want the mean, then usually we'll do like a mu. So mu will refer to mean in this class with the x. Okay? So just a couple different notations, depending on where you happen to be looking in the book, whether they will use e of x for expected value or mu of x for the mean of the random variable. And it means the same thing. If you have a discrete random variable, to find the mean, what you have to do is you take each x value and times it by its probability. The I means we're just going to sum them all up. You've all taken calculus, so hopefully you're familiar with this notation. So this is how you do it. You're playing a simple game with dice. If you roll an odd number, you get $1. If you roll a 2, you get $3. If you roll a 4, you get $6. And if you roll a 6, you lose $5. Okay. What we want to do is we want to figure out, well, what is your average? If you were to play this game lots of times, what would be your average winnings per game? Okay, are you going to come out ahead or losing money? And this is, for me, the easiest way to do it. Okay. I draw my table, and I put the x values, and I put the probabilities. Okay. So we're going to say that x is the money you get. What are the possible values for the money you can get? You can get $1, $3, $6, or you can get negative $5. And that negative is going to be very important that you remember it. What are my probabilities for each of those? What is the probability of getting a $1? Okay, it's an odd number, so the probability is 50%. Okay. What about getting the $3? $3. 1 6? The $6 is a 1 6 probability, and the negative $5 is 1 6. When you're done, what should those probabilities add up to? 1. So if I want to find the expected value, what I have to do is I times each x value by its probability. So the first x value is $1 times by its probability of 1/2. Plus my next x value of 3 times it by its probability of 1 6. The next x value of 6 times by its probability. And the last one, negative 5 times its probability. Let's see what that gives me. $1.16. What are my units on it? Dollars. Since that was $1 times unit list plus dollar times unit list, so my units are dollars. So my expected value is 1.16. Okay. So I expect to get $1.16. Now, as far as the interpretation, does this mean that when I roll the dice, I'm going to get $1.16 on that game? No. So, I mean, obviously, we never get $1.16 on a single game. since that's not one of the possibilities, how do I actually interpret this? Like, what would be an interpretation that would make sense?
Average gain.
The average gain, so, like, say a little bit more.
After playing a lot of games.
So, if I play a lot of games, what?
They'll average out to $1.16.
The average will be $1.16, and this is an important thing some people sometimes forget, per game. So if I played 10 games, how much would you expect to get?
$10, yeah.
$11.60. Okay, but on the average, if I do this many times, I'll get $1.16 per game. Now, people are usually okay with this, but then when I start asking you, like, what's the expected number of people that are going to walk through the door, and they say, I got 4.5 people, what did I do wrong? Well, it's okay to get half a person because it is just the average.
And is this just one roll per game?
Yeah, this was just one roll per game.
Okay.
Yeah, so one roll per game. Let's say I had 4 rolls per game. How would you find that expected value?
Times it by 4.
Just times it by 4. Or we could go back and think about the probabilities. But if each roll was just completely independent, like you just did the exact same thing 4 times, we could just times our expected value by 4. So, any questions here? This next one is where it really comes in handy. This is a very common use of expected value. You've heard of actuaries?
Yeah.
Right? Okay. This is, I'm not going to say what they do all day because this is going to be more advanced, but this is the basic foundation of what they do all day. Okay, so an insurance company sells a $20,000 life insurance policy for an annual premium of $300. Actuarial tables show that a person who would be sold such a policy with this premium has a 0.001 probability of death during a year. Let X be a random variable representing the insurance company's profit made on one of these policies during a year. Find the expected value of X, or the expected profit per year on one probability. So let's start this off by saying, well, what are my possible X values and what are my possible probabilities? Okay. Notice we want X to be the profit. Okay, so what are their possible values for profit? For just 1 year, what is the possible profit they can make? What do they make if you do not die and they don't have to pay out? Okay, they are going to make $300. So their profit could be $300. And what is the probability of them making that?
100%.
Okay, 0.999. Okay, and why is that? Because the probability of them dying is 0.001, and we know they have to add up to 1. Okay, so that was the profit if they stay alive with the probability of 0.999. What is their profit if the person dies?
They get 20,000.
-19,000.
Oh yeah.
Well, they pay out 20,000, but do they pay you back the premium? No. So what do they actually pay out? They are going to lose 19,700, right? If I calculated that in my head. So that's the biggest thing, is writing down your X values and probabilities correctly, looking through and trying to interpret what they told you in the problem statement. And now to find the expected value, we just take each X value, so like the first one is 300, times it by its probability of 0.99, plus the second X value, negative 19,700, and times by its probability. So I get 280. Now again, is there ever one person that they make $280 on? Exactly. It's their long run average. So $280 per person per year. Okay. So if you're selling millions or thousands or millions of policies, you're coming out pretty good, right? Now this is an interesting thing to think about just while we're talking about it. Let's say you're a very small company and you were just starting out and you only sold 5 policies. Okay, what do you think would happen to you, or what could happen to you? Okay. Well, if no one dies, you're okay, right? Because you're going to make $300 times 5, you made $1,500, you're happy, okay? But what happens if just one person dies? You're at negative 19,000 and you just lost all your profits and you're in debt, okay? Whereas if you're a big company and you sell thousands and thousands of policies, what happens if you just lose one policy here or one policy there?
No big deal.
It's no big deal because you made enough profits to compensate. So this is kind of a thing where expected value, again, only is going to make sense in the long run when you have enough time for your big numbers and your negative numbers to cancel each other out. Okay? And why it's a lot smarter to sell many, many insurance policies.
So an actuary, would his job mainly be determining what the actual percentage of likelihood of someone dying?
Yeah, so the actuary spends a lot of time trying to figure out the probabilities of someone dying. From what I understand, that is what they do. I've never taken a class, but I know a lot of the mathematical foundations that go into it, and so that's something that would be useful for them. And like it says here, they have the actuarial tables, and they have tons of tables. Like, so if you smoke, you're this. If you're this old, you're this. If you drive to work 5,000 miles, or drive 5,000 miles a year, you're this. So I think they have probabilities for everything. So how do you feel about that? That's not too bad, right? Not too mathematically complicated. That was the expected value for a discrete random variable. Let's do the expected value for a continuous random variable. Okay. So for our discrete random variable, let's remind ourselves the formula. It was the sum of each x value times each probability. Okay. Well, if you think about that, if you wanted to translate that from something that was discrete to something that was continuous, you're thinking of it as like the Riemann sums. Your rectangles are going to get smaller and smaller until you get to a nice curve, and we will end up, instead of doing a sum, we will do an integral. So the way that we do each x value times the probability and add them up is we're going to integrate, and we do x times f of x. That is the PDF, or the probability curve, dx. Okay, so the mean, or the expected value, is just the integral of x times f of x dx. And this adds from negative infinity to infinity, but if you have bounds on your problem, what do you really need to integrate from? Just within your bounds, because everywhere else the probability is 0. So, for this example, a certain criminal court judge hears many cases in which the defendant is found guilty of grand theft auto. And we've looked at this. We know that our probability density function, the PDF, is 1/9 x squared for x between 0 and 3. So we might be interested in knowing, like, what is the mean length of prison sentences given by this judge? Mean length means find the expected value. So I might say find the expected value. I might say find the mean. Either way, you're going to do the same thing. Okay. So you integrate. What should I integrate? What should be my bounds? 0, 2, 3. And my formula is I'm going to do x times the PDF, which is 1/9 x squared dx. At this point, I'm going to start just putting the integrals into my calculator instead of trying to integrate and show everything. If you need help with integrals, you're welcome to come to office hours and let me know, but we won't spend a lot of time on it in class. So I get 9/4 or 2.25. So if we consider many sentences, so if he's given out several sentences already, or he might give out hundreds of sentences in the future, we expect that the mean length will be 2.25 years per person. So I really like the formula for expected value because all you have to do again is just x times your PDF, put it in your calculator, you're done. So that was just the expected value. We might change things around though. We might say, well, let's say we have a function of a random variable. So our function is h of x. So we have h of x of our random variable, and we want to find the expected value. Okay. The way that you find it is you can do this for discrete or continuous random variables. It doesn't matter. This will work either way. So if you want to find the expected value for discrete, then instead of just putting each x value times the probability, you would just do the function evaluated at x times the probability value. So it's just going to be h of xi times pi. If you want to do it discretely, then it's just going to be h of x times the PDF dx. So h of x will just be your function, and f of x is your PDF. So let me show you how this plays out. It's really simple when you actually try it. So remember that the sentences given by a second judge have this distribution. Okay, this is my PDF. Suppose someone decides that instead of using the sentences given by this judge, they would square the length of the sentences and add 2. I just randomly made this up. Don't try and think too much about it. What is the new expected length of sentences? So how would you write this function? What are they doing to my original y value? So we square the length of the sentences and add 2. So this is my function. So every sentence gets squared, you add 2 years, and we want to say, well, what is my mean value now? Okay, what is my expected value of these new sentences that follow this formula? Okay. So maybe they decided the second judge was too nice or something. They need to make the sentences longer. If you want to find the expected value, so if you want to find the expected value of y squared plus 2, what you're going to do is you're going to integrate. What will my bounds be to integrate?
0 to 4.
It's still going to be 0 to 4. And instead of putting a y here times the PDF, I just put a y squared plus 2 and times it by the PDF. So notice this is just my function. This is my PDF. You just times the function of what you want to find the expected value for, times the PDF, and you're good. So 8.85. Remember what we learned on Thursday? I fully expect you guys to tell me if you get something different. So, any questions on our expected value so far? Now, I would have chosen to put this here, but the book puts the median in this section. Okay? So the expected value is our average or our mean. And thinking back to other math classes you've taken in the past, what other ways do we like to describe the middle of a distribution? We use the median. Okay? Now remember, your median is your middle value. Usually we say half the observations are below it, half the observations are above it. Okay? If we're talking about just probabilities instead of observations, then the way we define the median is we say, okay, if it's the median, then that means half the probability has to be below it, half the probability has to be above it. So you can say like the probability that x is less than or equal to a is 0.5. Or the probability that x is greater than or equal to a is 0.5. So again, half the probability below, half the probability above. The easiest way to find this, okay, some books try and make it really complicated. It's not complicated to find the median. If you want to find the median, you take your CDF, set it equal to 0.5, and solve for x, or any other random variable you want to put in there. Okay? Because if half the probability is below that point, then the CDF, the cumulative probability, would be 0.5. So on your homework, if you want to find the CDF, just set, or your median, set your CDF equal to 0.5 and solve for x. Very simple. And then on the last page, okay, you can look through these carefully, but I just kind of wanted to show you graphically what the expected value looks like. Okay, so these first four, notice they are all these line graphs. That means that they are discrete random variables because you only have so many possible values for x. Okay, and notice like where the expected value falls. Like I just want you to get this intuitive sense of where the expected value would be. Okay, and this is why it's a weighted average. So for example, like in the second graph where we have the cost can be 50, 200, or 350, notice that my expected value isn't like in the middle, but it's further over to this side because I have a lot more probability attached to that point. So just look through those and see, well, where does the expected value seem to fall? And you'll notice it is this weighted average. So where this x value of 8 has such a high probability, it pulled the expected value, or the mean, a lot higher. And if we threw in a few continuous distributions, so we have a curve now, notice again, like where does the expected value fall? Like does it get pulled to a side? Is it in the middle? Okay, just kind of look at these. By the time you look at lots of them, you'll kind of get this intuitive sense. And then there's one more point. So this is just something that I want you to have seen once. Okay, so if you have a distribution that's symmetric, okay, so here are examples of symmetric distributions. Okay, notice they're all symmetric about this middle point. Okay, I'm just going to call the point A. Then the mean and median will be equal to A. So the weighted average and the middle point, okay, half above, half below, will all be equal to that symmetric point. Okay, so for this example, here's my symmetric point, so my mean is going to be 50. And in this one, your mean is directly in the middle, and so is your median. Okay, and here again, your mean and median will be this point where it is symmetric. The reason this is useful is there are actually some PDFs that are impossible to integrate, and if you can't actually integrate them, it's difficult to find the expected value. But if they are symmetric, once they're symmetric, you can figure out where they're symmetric and find the middle point. Okay, who's heard of the normal curve? Okay, the bell curve. Okay, so if you've heard of the normal curve or the bell curve, that is an example of a distribution where the PDF is impossible to integrate. Okay. However, we know it's symmetric, and it's symmetric about its mean, and so we can find the mean that way. So, any questions on section 2.3? You know enough now to do all your homework for 2.3. Okay, when you get home tonight, start working on it. So, section 2.4. We've talked about the mean or the expected value. Now we're going to do the variance. Okay? The variance measures the spread or the variability in the values taken by the random variable. So the variance for a random variable x is defined to be this. Okay? Looks long and complicated. So the variance of x is the expected value of what you have to do is you have to take x minus the expected value of x, which you've already found, or you have to find first. And then you square that, and then when you're done, you take the expected value. Okay. Or, we've learned in the past that we can simplify this to you take the expected value of x squared minus the expected value of x all squared. Okay. So two different formulas that are possible to use. Okay. And it does look complicated. We'll practice doing it with the actual formula so you can see what it looks like. A few things to know: the variance of x is always greater than or equal to 0. Okay. The variance measures the spread of the distribution about the mean value. So you find your mean value and you say, how far are my points from the mean value? And larger values of variance indicate that the distribution is more spread out. Now, I'm sure you've all heard of standard deviation before. The standard deviation, to find standard deviation, all you do is you take the square root of the variance. So standard deviation, just take the square root. Now there's a few alternative symbols that we can use. So the mean, we can do e of x, or we can use a mu. Variance can be var x or sigma squared. And for some reason, we've never tried to, so like this is e of x and var of x, we've never come up with something like that for the standard deviation. I don't know why, but the mathematicians haven't. So the only symbol we've ever used for standard deviation is this sigma. So I wrote the formulas for variance up above. These are the formulas, that's more the theoretical. Here's the formulas of how you will actually find it. Okay, so if you want the standard deviation for a discrete random variable, okay, first thing you have to do is you have to have found the mean. Okay, then you're going to take each x value minus the mean, square it, times it by its probability, and add them up. If it's continuous, you will integrate, and you'll do x minus the mean squared times the PDF and integrate that. And then, before we actually do an example, okay, here's just a little graphic to talk about the differences between means and variances. Okay, so when I look at this first graph, okay, how would you compare the means of the distributions for these first graphs? Like, where would the means fall? Okay, they seem to be symmetric, so the means would be in the middle of each. Okay, so in this situation, my means are different. Okay. What about, so we can have different means. What about the standard deviations or the variances? How are these data spread out? It seems to be the same. They both have like the same width. The data seems to be distributed the same way. So we have variances are the same. What about for my second graph? What would you say about the means?
Means are the same.
So means are the same. Okay, what about the variances? So my variances are different. Okay, so let me pick just this graph. Okay, would you say this red line, it has a bigger or smaller variance than the other one? Okay, so the red has the bigger standard deviation or bigger variance. Because my data values are further spread out, it's stretched out more, all the observations are further from the mean. And so this is why, even though the mean is a lot easier to find, we often, for any random variable, are going to want to find the mean and the variance because they tell us different things. You could have things that have the same variance and different means, or same means and different variances. And so it's important to know both things for random variable and not just one. So let's try it for a discrete random variable. Okay. So from past experience, Linda knows the probability distribution for her car sales. Find the standard deviation of the number of cars she sells. Okay. What is the first step before I can find a standard deviation or a variance? We have to know the mean. So mu, or the expected value, whichever way you want to think about it, is I have to take each x value, times it by its probability, and add them up. So, first x value for number of cars she sells would be 0 times 0.3, plus 1 times 0.4, plus 2 times 0.2, plus 3 times 0.1. Okay, so we expect that in the long run, the number of cars she sells, the average will be 1.1. And I guess I should say that this is like per day or something. I didn't say that. So in the long run, the average will be 1.1 cars per day. Okay. Once I have the expected value, now I can try and find my variance. Then once I have the variance, then I can try and find my standard deviation. So as part of the variance, I know that I need to add up each x value minus the mean squared times the probability. So that's what I'm going to do in the table. Makes it easier for me. So I'll take my first x value of 0 minus my mean of 1.1 times it by its probability. Oh, and I forgot my square. The next one will be 1 minus 1.1 squared times 0.4. The next one, 2 minus 1.1 squared times 0.2. And the last one, 3 minus 1.1 squared times 0.1. And I'm going to put each of these in my calculator, see what I get. Why is that second one for 1 minus for the 1 so small? It's really close to the mean. So this is each x value minus the mean squared times the probability. So if I want my variance, or sigma squared, what do I need to do with all of those values?
Square root.
Okay, well, so for my variance, I need to add these values up. So it is the sum of xi minus mu squared times the probabilities. So 0.363 plus 0.004 plus 0.162 plus 0.361. .163. That is my variance. Now I want the standard deviation, okay, sigma, and to do that I just have to take the square of the variance, the square of 1.163. .078. So that is my standard deviation. So I found my mean, I found my variance, I found my standard deviation.
So mu is the mean.
Uh-huh.
Okay, and then 1.161, 1.163, sorry, is the variance.
Yep.
Okay.
And then my standard deviation is my 1.078. So one of the big reasons that we have variance, and that measures the spread of our distribution about our data. One of the big reasons that we found standard deviation and people like to work with standard deviation is it gives us good units. Okay, so if we think about this, our units here is number of cars sold. Okay, and like when we find our mean, it's number of cars times the unitless number plus number of cars times the unitless number, and so my units end up being cars. And it makes sense to say that the average is 1.1 cars per day. When you think of the variance, what's happening to my units here? I have like 0, so 0 cars minus a number squared, or 0 cars minus 1.1 cars squared. So I end up getting units of cars squared. And does that mean anything to you? Does units of cars squared mean anything? Okay, it doesn't. And so units for variance usually don't make sense. Okay, and so what they said is, well, if we just take the square root, we'll be back to normal units, because this is technically cars squared, and this is units just cars. Okay, and I know a lot of time in our math classes we get lazy about our units and we don't actually keep track of our units, but if you've ever taken a physics class or something, do units matter?
Yeah.
Quite a bit. And so when we look at this logically, we want to have units that make sense. So expected value should be cars, and then standard deviation will also give us units of cars. And I think that's one of the biggest reasons that we decided to use standard deviation and not just variance. So, any questions on how we calculated it? Okay.
When I added up those four numbers, I got 0.89.
Let me try again. Thank you. Maybe I missed the 0 on my 0.004. Okay. So this is 0.89. And the standard deviation is the square root of 0.89, which gives me 0.943. Now, when I'm in the classroom, I expect you guys to catch my mistakes when I type in the calculator wrong, because y'all are typing as well. On the test, that is not a good reason to miss points on the test, because when I take a test, what do? I double check and triple check everything myself. So just because I make mistakes up here doesn't mean that I don't take points off on the test.
So I have another question. This may be silly, but like, so the probability of that from the initial like 0.3, selling 0 cars 0.3, would that be like her, or yeah, that Linda like keeping track over the course of like months, and she realizes that each day it's not just something that she thinks of?
Yes. So, like we said at the beginning of our probability section, there's different ways to find probability. Like some would be logically. Some are you just, and then really, or, okay, so you can do it logically, you can do it long-term frequency, or you can use your best judgment. Okay, so realistically, this would either be, I think this would be after weeks or years of selling, she realizes that these are her probabilities as a long-term frequency. Okay. Because there's, I don't think, any logical way that you could come up with that. Any other questions before we try it with a continuous random variable?
Yeah, sorry, I have another question. I don't know.
That's okay.
I don't understand, like, what the, at least in Linda's situation, what value she has getting the standard deviation. Does that make sense?
Yeah.
Like, why would Linda want to know about the standard deviation?
Okay. Linda, as a car salesman, probably won't care.
Okay, because she probably wants to know how many cars she'll sell.
She'll sell on average.
Yeah.
Okay. However, it's useful in many situations. It doesn't have, so people are always looking for a very direct application. Like, so if my standard deviation is this, if I times it by 2, that will tell me my bounds for how many cars I sell or something. And it doesn't have like a very distinct application. I can't tell you what it is on a graph if I look at it. I can compare two graphs, but it doesn't have a very direct application. But we could, like, it's always useful to compare things, I guess. It's usually not very interesting by itself, but it's interesting to compare two things. So let's say that these are the two distributions for taking your car into a garage. So let's say this is the amount of time it takes at garage 1. And let's say that this is the amount of time it takes in garage 2. Okay, which garage is faster? Okay, so tell me, just what are your thoughts? Which garage is faster?
Average garage.
Okay, so you think garage 1 should be faster on average? So garage 2 is slower on average, but does garage 2 sometimes end up being a little bit faster than garage 1? So if you end up here, you might be faster than garage 1. But garage 1 is usually faster than garage 2. So this is an example of like where garage 2 has a lot more variance, and it kind of comes down to like, are you a risk taker? Would you rather go to garage 2 and if you're lucky, you'll be faster, or would you rather go to garage 1 and you know that all of the values are very centered, very close together, and figured that on average you should be faster? So it's, again, very useful for comparing two distributions to see like which one is going to be more spread out, or like which one is riskier versus, but it's really hard for me to just look at garage 1 and say, oh, I think that standard deviation is like 5, and then it doesn't really mean anything to me. Does that help?
That makes sense, yeah.
I'll look that up there, yes. And we will deal with standard deviation a lot for the rest of the semester, and you'll look at it, and we'll do it with like observations, and it'll start to sink in a little bit more too. But realistically, Linda probably doesn't care that her standard deviation is 0.9. Actually, let's think about that a little bit more. So let's say that Linda has a standard deviation of 0.9, and let's say that there's another salesman there that has a standard deviation of 2. Okay, how would you then describe these two salesmen?
Wouldn't they be more steady and more constant or consistent?
Yes. Linda's more steady, more consistent. Like, she might not sell as much as this other guy, but you know she's going to sell about 1 car per day, every day, like on average. She's there, she works, and this other guy, Tom, some days he doesn't sell at all. He probably just skipped work and didn't come in. Some days he's really good and he sells like 5, but he's not very consistent. Now that was discrete. Notice, was it kind of a lot of work to find a discrete variance? It took us a little while. And that was with only 4 possible values. Can you imagine if this had 500 possible values? It would be a pain, right? This is why I like, again, continuous random variables, because I can use my calculator, integrate once, and I'm done. So let's try it here. So again, we have this PDF. I don't need to read the problem statement again. This is the length of our sentences, and it's length in years. Okay, find the variance of the length of the sentences. Okay, if you look way up on your page, or on the previous page, the variance for x, or we can use the symbol sigma squared. What we do is we integrate, and we do x minus the mean squared times the PDF. So let's see what that will be in this situation. So I need to integrate. What should my bounds be? 0 to 3. Okay, so you integrate over your entire region. X minus, have we found the mean for this already previously? On previous packets. I'm pretty sure we have. If you flip back, do you see it?
2.25.
What is it?
2.25 years.
2.5?
2.25.
2.25? So we knew previously that mu equals 2.25. How would I have found it if I didn't know from previous? I would just integrate x times my PDF. So it's going to be x minus 2.25 squared times my PDF, so 1/9 x squared dx. So again, just x minus your mean squared times your PDF. And put it in your calculator. So the variance is 0.3375. How do you feel about that? So, for example 7, let's do the same thing, but this is for the second judge. He has a different PDF. We want to find the standard deviation this time. Okay. So let's actually write it out. So let's say that you didn't remember what the mean was. So to find my mean, I would need to integrate from 0 to 4 of x times my PDF. So, but I'm not using an x, I'm using a y. So y times 3/16 square root of y dy. Let's see what my mean is. .4. So my mean is 2.4. So if I want to find my variance, I know I need to integrate from 0 to 4, and what's my formula? I need to do y minus my mean, which is 2.4, square it, and times it by my PDF. So I get 1.097. Am I done? No, they told me to find the standard deviation. How do I find the standard deviation? Take the square root. .047. Now, if you told the reporters that the standard deviation for this judge was 1.047, is that going to mean anything to them? Probably not in and of itself, but if you told them that the variance for one judge is 0.33 and the variance for another judge is 1.09, which judge is more consistent in their sentences? The first judge. He has a much smaller variance. Whether or not you think that's a good thing would be up to you, but you can tell that the first judge is more consistent in his sentences. Any questions on this method for calculating the standard deviation? Okay. I am going to show you method 2. Pick a method you like and stick with it. Don't try and switch back and forth. Okay? But if you ever go into another class or something, this would probably come in handy for you if you've seen it once. Okay? It's very useful because it's actually easier to calculate usually. So if you remember on the very first page, I said you could also calculate the variance of x as the expected value of x squared minus, you take the expected value of x and square that. Okay? And so this is actually a much easier formula to calculate in some situations. And it's very common. This is actually the way that most people do it, even though it's an extra step to memorize. And so what you do is you calculate the expected value of x squared. And to do that, we still integrate from 0 to 4, but I just integrate x squared times my PDF. Okay? But instead of x's, they should all be y's. So the expected value of y squared is just going to be y squared times my PDF. So 6.85. And did we already calculate the expected value of y? We knew that the expected value of y, we already calculated that, integrating from 0 to 4, of y times my PDF So 2.4. Okay, so if you have both of these numbers, okay, then you can plug them into this formula. So the variance of y is the expected value of y squared, so 6.85, minus the expected value squared. Let's see what that gives me. So I get 1.09714. Okay, which is that the same thing that I got the other way? Okay. So both methods I got 1.097. So again, for this method you can just find the expected value of y squared, find the expected value of y, and use that formula. Why do you think I would want to use the second formula instead of the first formula? What are any possible benefits that you can see?
You don't need the mean.
Okay. Well, this is the mean here, and technically that's my 2.4, and I did have to still find my 2.4 here. So I still have to find my 2.4. The difference is, just as far as integration goes, is it easier to integrate if you had to do it by hand? Is it easier to integrate this y minus 2.4 squared, or to just integrate this y squared? It's a lot easier to integrate this. So if you didn't have a calculator, that's why people like the second formula, is it's just easier to integrate by hand. Otherwise, I mean, they do the exact same thing. So pick the one that seems more natural to you and go ahead and use that. Okay? But you do need to at least have seen both in case it ever comes up in another class. Okay. So questions on variance?
Can you say from the variance without going to the standard deviations that, like, do we ever focus on that? Or do we initially always go towards the standard deviation?
Standard deviation is nicer because you know the units, or units make sense. Lots of times, though, people will tell you the variance, or you will ask for the variance. Really, you should be comfortable with both because it is easy to go back and forth. So later on in this class, we'll do problems where you need the variance for a formula, and I give you the standard deviation, and you have to convert, or I give you the variance and ask you for standard deviation and ask you to convert. But as far as real-world applications, you could tell your boss either one and be okay unless he'd specified. Okay. Other questions? So that is how you find variance. Now, variance is one way to measure the spread of the data. There are other ways to measure the spread of the data. Like, do you remember other ways from math classes? Like how you measure the spread of a data set? There's range. Like, how did you find range?
It's like max and minimum.
It's the max and min, so take the max minus the min, and that tells you the range. Do you remember anything else? Like, any other kinds of ranges?
What's the domain, too?
Okay. Oh, so like as a math, when we talked about functions, we had domain and range. If we're talking about statistically, though, we just have a data set. We care about the range, and then we also care about the like interquartile range. Or do you remember doing box plots? Okay, so box plots, you had like your first quartile, third quartile, things like that, and that was dividing quartiles, divide your data up into 4 pieces. Okay, so those are all different ways that you can also measure the spread of the data, which is why this is in this section. Okay. So variance isn't the only way, but it is the way that statisticians prefer. Okay. But here are some other ways that we can describe our data. So percentiles, quantiles, and quartiles. So percentiles, quantiles, and quartiles all provide information about the spread of a random variable. Okay, the pth quantile is the value of x for which f of x equals p, or the probability that x was less than or equal to my pth quantile equals p. Not point B, just p. So it's the value of x for which we have p probability below it. So if I want like the 0.37 quantile, I'm looking for the area that has 0.37 below this x value. Okay, so what x value has 0.37 below it? We can also, usually we like to say percentile instead of quantile. So if you're in the 37th percentile, what does that mean? 37% is below you. Have you gotten a lot of standardized test scores where they gave you a percentile? So if they said you're in the 87th percentile, that means that 87% of the people had scores below you. Okay. So the lower and upper quartiles, or the first and third quartiles, refer to the 0.25 and 0.75 quantiles, or the 25th and 75th percentiles. The median would have to then be the 0.5 or 50th percentile, since half the value is below it, half the value is above it. And remember, to find the median, we just set f of x equal to 0.5. So if I wanted to find, say, the 0.37th percentile, what would I want to do, like, compared to this? Make it 0.37 and solve for x. So we're going to try it. So a PDF, this is my PDF, and it is valid for x between 0 and 10, and then my PDF will be 0 otherwise. The first step, if you're going to want to find a median or a quantile or percentile, is to find your CDF. That's the easiest way, is find the CDF first. So here's my PDF, let's find my CDF. How do I go from PDF to CDF? Integrate. What are my bounds? Okay. So this is where I have to be careful. So when you want to find the CDF, I need to end up with a variable in there and not just the number. So I need to make sure I'm integrating to x, but my lower bound is 0. And I take my PDF, so I just need to integrate my PDF. I need a dummy variable, like t, so t squared dt. So this gives me x cubed over 973 for, what are my bounds going to be on my PDF? For x between 0 and 10. Why is this? This is still not a valid PDF. What are the rules to be a valid PDF? Greater than 0 and oh wait, no, that might be right. If I integrate the original PDF, I was just double checking since I made the mistake earlier today. So if I integrate my PDF, it should integrate to 1. And it doesn't integrate to 1. I swear I just took this one out of a book. We need to do 3 out of 1,000. Don't ask me why they did something that wasn't a valid PDF. Okay. Let's try that. If I do 3 out of 1,000, then it will actually integrate to 1. Sorry, I apologize for this. I will make sure in the future that they are all valid PDFs. I just didn't bother checking things I got from books. Okay. It doesn't change how I find the CDF, but I wanted to make sure that it actually was a valid PDF to start with. So that is my CDF, x cubed over 1,000. what is my median? How would I find my median? Set my CDF equal to 0.5 and solve. So x cubed over 1,000 equals 0.5 and solve. So x is going to equal -7.93. Everyone else? Okay, so my median is 7.97. So half the probability is below that number, half the probability is above that number. So if I want to find the 0.37 quantile, what is the only thing that changes? Set f of x equal to 0.37 and solve for x. So we're going to have x cubed over 1,000 equals 0.37. So x equals 7.179. Okay, so that means 30% of all the data is below x equals 7.1. Okay. So again, like I said, some books try to make this really complicated. It's not complicated. Just set your PDF equal to what you want, or your CDF equal to what you want, and go for it. Pretty simple. Questions on the quantiles? Then the next thing that we want to be able to do with random variables is do combinations of them. Okay, this is where it gets interesting. Okay, so your combinations and functions of random variables. Okay. So you have rules for means. So rule 1, if x is a random variable and a and b are fixed numbers. Fixed numbers means that they are constants. Okay. Then the expected value for ax plus b. Okay. What you do with this is the a, if it's the coefficient, comes out as another coefficient, so it's just going to be a times the expected value of x plus b. So you just add your constant in. Whereas if x and y are just random variables and you want to find the expected value of x plus y, you just add the two expected values. That seems very intuitive, right? It's what you would want to do. So this is the linearity of our expected value, or our means. So let's try, for example, 9. So we haven't talked about the variances yet, but let's try the means and see how these rules feel to us. So for example 9, we have these random variables, x, y, and z. They are independent. What does independent mean? Do you remember?
The outcomes are influenced by each other?
Yeah, they don't influence each other. Okay, we have the expected value of x equals 1, expected value of y is 2, expected value of z is 3. We want to calculate the expected values, variances, and standard deviations of these following new random variables. Okay, so we'll go through and just find the expected values for all of them, and then probably tomorrow we'll go through and find all the variances for them. So for the first one, u equals 8z. So what we're doing here is we have our old random variable z. And we want to make a new random variable. So this could be something like, if z was the number of cars that Linda sells, what if she gets, or she works for 8 days? We would want the expected value of how much she makes over those 8 days. And intuitively, when I asked you guys this before, you just said that you would, if she makes 1.1 cars per day, or sells 1.1 cars per day, then over 8 days, what would you do to find the expected value? Just times 1.1 by 8. Okay, and so that's what we're going to do here. So if we want the expected value of u equals 8z, then the expected value of u is going to be 8 times the expected value of z. Okay. So again, this 8 just gets to come out. And look up above, what was the expected value of z? It was 3, so the expected value of u is 24. So again, your expected value just, if you have a coefficient in your expected value, it just comes out as the coefficient. Okay. For the next one, v equals y minus 6. So the expected value of v, that's really the expected value of y minus 6. And this minus 6, what I get to do is I just say, well, I'll just find the expected value of y and minus 6. So what is the expected value of y? 2 minus 6 gives me negative 4. What about number 3? So we have the expected value of w. So this is my 6x plus y minus 5z minus 7. Okay. So if I start writing this out, what's going to happen with my 6x? I just need to do 6 times the expected value of x. Okay. Plus y, so just the expected value of y. Okay, what about this minus 5z? Minus 5 times the expected value of z. And the minus 7, I just minus 7. So I always like to tell my students, as you go through here, the expected value is nice because it behaves like you would want it to. So where you have your minus 5z, it just seems intuitive that you want to minus 5 times the expected value of z. So let's plug everything in. So 6 times the expected value of x is 1, plus expected value of y is 2, minus 5 times the expected value of z, so 4 minus 7.
Expected value of z is 3.
Oh, I looked at the variance, thank you. Expected value of z is 3. So negative 14, anyone else? So, you have questions on that? So those are the rules for means. Okay, so now we have to figure out, well, what happens if we want to talk about the rules for variances? Okay. So for variances, if x is a random variable and a and b are fixed numbers, then the variance of ax plus b. Okay. Well, for this a, it's going to come out as an a squared. Why do you think it comes out as an a squared? Okay, because variances, the symbol is sigma squared, and when you think back to the formula for variances, what were we doing in the formulas? We were taking each x value and squaring it. So when you think about it that way, if you took each variable and times it by your coefficient a, so I took each variable, times it by a, so let's say a is like 3, so if I take each variable, each x value and times it by 3, then when I go and plug it in, it's going to be 3 times x minus the mean squared, and so that 3 gets squared each time, and so that's why it comes out as my a squared. So for your variances, you need to be careful. If you pull out your coefficient, it comes out as an a squared. So a squared plus b. Notice, do you see any b's here? Okay, no. Okay, why do you think that might be? Okay. So let me draw a picture again. So let's say that this is my original function. Okay, so this is x. Okay. If I want to do x plus 7, okay, what would it look like? What would change in my PDF?
It's a shift over 7.
It's just going to shift over 7. Okay. Notice, did my variance change at all? And it shouldn't. Because if you're just adding a number, all you're doing is shifting it, and that's not going to change the shape of the distribution. It won't change how spread out it is, so the variance should be exactly the same. So that's why when it says in here, if you add b, nothing changes. So a shift does not affect your variance. Does that make sense intuitively? Now, if x and y are independent random variables, again, they don't affect each other, then the variance of x plus y is the variance of x plus the variance of y. Okay? This only holds if they are independent. Otherwise, it's not going to work. Okay? There is another formula for if they're dependent, if they do affect each other, but it requires things that we're skipping in this class, so we're not going to do it. So this formula works if they're independent. And then if I ask you to find the standard deviation, what are you going to do? Take the square root of the variance. Which means for most of these formulas, the problem itself will say find the standard deviation, but you have to remember first I need to find the variance, then I will go back and find the standard deviation. So let's try it for this problem. So u equals 8z. So we want to find the variance. So it's the variance of 8z. Okay. So what happens when I try and pull out that 8? It comes out as 8 squared times the variance of z. So 8 squared times 4. The variance of z is 4. So 256. And how would you find the standard deviation? Take the square root. Gives me 16. Again, you'll notice there are no formulas for standard deviations, so if it asks for standard deviations, you have to do it in variances first. Okay. So this next one, so for v equals y minus 6, so if I want to find the variance of y, of v, well, that's the variance of y minus 6. What happens to it if you just minus 6? So if you take your whole random variable and minus 6, we just shift it all down 6, what happens to the variance? It doesn't change. This is just the variance of y, which is 6. So for the standard deviation, I take the square root of 6, which gives me 2.449. And the last one, so we're looking for the variance of 6x plus y minus 5z minus 7. What happens, let's start with the 6 first. What happens to the 6?
Squared.
It comes out. Now, what do I get to do with all these pluses and minuses? Do I have to concern them all together, or can I separate them out? Okay. Because they are independent random variables, then I can do the variance of the x part, and then plus the variance of the y part, etc. So this is going to be 6 squared times the variance of x. Plus, let's see, for the y, that's just the variance of y. Okay. Now, this next part is important. Okay. What should I do with this minus 5?
Comes out as a positive.
Okay. It's going to come out, and this is technically, couldn't you write minus 5 as plus a negative 5? Okay. So this is going to be plus, and then what happens to that negative 5? It comes out squared. Okay, and so what is going to happen to that sign? It is going to become a positive. Okay, so again, that's very important. And what about that negative 7? Does it do anything? No. Okay. So again, very important, if you have a minus, treat it as plus a negative and make sure you are squaring that negative. So this is 6 squared times 3 plus the variance of y is 6 plus, let's see, negative 5 squared times the variance of z, which is 4. Anyone get an answer for that? $214? That's 6. That's 25 times 4. Yep, 214. And find the standard deviation, we take the square root.